Good morning. My name is Jeannie Montblanc. With me is our co-coordinator, Corey Gooker. And on behalf of the Great Basin Fire Science Exchange and our partners, I'd like to welcome you to this webinar and discussion titled Insights from Wildfire Research, Air Quality, Monitoring Technologies, and Post-Fire Soils. Our presenters today are Meghan Collins, Conor Croskery, Bianca Martinez, and Jehren Boehm from the Desert Research Institute and the University of Nevada, Reno. Before I introduce the presenters, I'll go over some webinar details. We're using Zoom Meeting as our platform with attendees' mics and cameras off. We'll use the chat for questions, so please type in your questions at any time and I will field them to the speakers. We'll answer a couple of questions directly after each presentation, and after all presentations, we'll open up the meeting for more Q&A and discussion. Now, I'd like to welcome our presenters from the Desert Research Institute and from the University of Nevada. Meghan Collins is an associate research scientist and a science communications lead with the Desert Research Institute. She specializes in science communication and translating research into practice and has been with DRI for 10 years. Conor Croskery is a recent graduate from the hydrology program at the University of Nevada, Reno, and is working at the Desert Research Institute as a research assistant. He has worked with the hydrology and ecology components of the HDRFS project, which we'll hear about in just a minute, as well as other snow and soil-related projects in the Sierras. He has experience studying soil hydrology in this area and how it is affected by wildfire. Bianca Lee Martinez is a PhD candidate in the Atmospheric Science Division at DRI. She has been working in the HDRFS project under the Fire Emissions and Atmospheric Aging FEAA component. In this component, Bianca has been studying biomass burning of the shrubland landscape, specifically assessing the chemical emissions from the smoke in the sagebrush ecosystem. Jehren Boehm is a PhD student at the University of Nevada, Reno in the Department of Geography. His work is focused at the nexus of environmental monitoring and technology as part of the Research Engineering Lab within the Nevada System of Higher Education's System Computing Services Group. Holding a Master's of Science with a focus on dendrochronology, Jehren has experience in Great Basin paleoclimate science and an interest in long-term monitoring of ecological response to climate weather extremes. Welcome all, and thank you for presenting today. And now I'll hand it over to Meghan.
Thank you, Jeannie, and it is an absolute pleasure to introduce the three students and professionals. I will give a brief overview of the Harnessing the Data Revolution for Fire Science project before we dive into their respective topics. HDRFS, or Harnessing the Data Revolution for Fire Science, is a 5-year research project funded by the National Science Foundation to advance understanding of wildland fire in sagebrush ecosystems. The project team consists of fire ecologists, hydrologists, experts in fire processes, smoke chemistry, and more. But these fields rely on critical advancements in cyber infrastructure, advanced environmental monitoring, autonomous systems, and data science. So what is unique about this team is that it is advancing the physical sciences, the technology, and our ability to process data so that we can deepen our understanding of wildland fire on the landscape with these interdisciplinary advances. As part of this brief introduction, I want to share a short video that tells you how these elements fit together, and then we will hear from our speakers.
Harnessing the data revolution for fire science has a few major pieces. We were looking at building infrastructure for wildland fires within the state, and also to be able to help train the next generation of researchers, and so that we can actually grow as a state to be able to do better research. If you look at the wildfires throughout the US, the top area is Nevada and its neighbors. That's one of the reasons we picked this project to start with, because that is where the wildfires are. We have a huge open area in the Great Basin, and the sagebrush ecosystem is a major point of that.
It's a project funded by a National Science Foundation. And in this project, our goal is to increase the capacity of Nevada in research, education, and workforce development, specifically in the area of wildfires and targeted to the very specific ecosystem of sagebrush.
We have two major components that are during the events. So you have the fire emissions, we have fire process modeling. So we're modeling the fires and we're also measuring smoke. Then we have two major science components that are between the events, ecology and hydrology. They're trying to find out what things happen and change between the events and how fast they change. Then we have the last science component is the cyber infrastructure innovations. They're doing a lot of things with regards to drones to collect data during the events, machine learning to be able to process the visualization, and helping tie all these pieces together.
Today, we will hear from 3 HDRFS team members who will share perspectives on hydrology and post-fire soils, chemistry of wildfire smoke, and the environmental monitoring technologies that make this research possible. As Jeannie mentioned, our presenters are graduate students or recent graduates who are tomorrow's leaders in these fields and hopefully future colleagues of yours. So we are looking forward to the conversation that will happen after their presentations. And with that, I will bring on Conor, who will kick us off.
You're still muted, Conor, just so you know.
Thank you. I am sharing the screen.
Looks great.
Presentation. Cool. Alrighty, so good morning, everybody. I'm Conor. So the topic we're going to be talking about today is understanding the relationship between soil hydrophobicity and fire in sagebrush ecosystems. This is as we already went over, it's the HDRFS project, NSF funded. But so just kind of as like a brief introduction, this is the hydro team over here, just an example of one of the plots we burned. But in the hydro section, in the hydrology section, what are we looking at? We are looking at specifically hydrophobicity. And so like the soil water repellency and how that changes based off of fire. And so hydrophobicity caused by fire is a well-observed phenomenon. We know that after wildfires, the soil tends to become more hydrophobic, and this has a lot of greater reaching consequences, right? So it seems like a small thing, but it affects how much water gets stored into the soil, how much water infiltrates in, and that can cause other things like in specific areas, increased erosion, which could lead to decreased water quality. And so it is an important topic, and it is important that we know how the mechanisms are working and how to predict how the hydrophobicity is being formed and where it's being formed after wildfires. But the problem is that most of the studies that we have on this are only in forested ecosystems. We don't really have any in sagebrush ecosystems. And so that's kind of the main draw of doing this study, is that we get to do all these experiments and get all these measurements from specifically a sagebrush ecosystem. And also the other unique thing about this too is that we have measurements before a fire and after a fire. All the plots that I'm about to show you are set up on a grid system. And so you know exactly where we took all the pre-fire measurements. And so we're going to go back and take all the post-fire measurements and see if it was hydrophobic before, is it still hydrophobic after, vice versa, and how that all changes, right? And so jumping into this, we have just an introduction to the Red Rock Road site. It's north of Reno. The site was chosen because it has a pretty good representation of the plant species that you would find in most of Nevada. It doesn't have too much infiltration of invasive species. But one of the other good things about the site is that the whole area burned in 1980, right? But then you can see on this kind of scar right here, it burned again in 2020. So that means that we have a transect where we can test a more recent fire and an older fire. And we have 20 plots set up, these little boxes right here, and they're color coded because they are set up they're grouped in pairs of fuel load and plant communities. So with the idea being that if we burn one, we'll have a control for the other. So we can kind of observe how each is changing through time, if it didn't burn versus if it did burn, and how that affects them. And so jumping into just some overview of the measuring devices and tests that we're doing. So the main test that we do to show hydrophobicity on the soil is the water drop penetration test. This is just a picture of some water drops on some very hydrophobic soil. This isn't at the Red Rock Road site, but it is from the Red Rock Road fire, which recently happened this past year. We also went out there and collected samples from there, and it's a good picture. It shows how the water balls just beat up on the soil and will sit there for minutes at a time if it's hydrophobic. And so that's the main test that we do for hydrophobicity. Some of the other tests that we're doing too, because we want to relate the hydrophobicity to other physical aspects of the soil and see how that changes. So if like soil moisture is the amount of water in the soil, does that change based on the hydrophobicity? Does it increase it? Does it decrease it? And then ultimately, does that affect the plant species above it? And also, is it affected by the plant species if we're testing, say, under a shrub versus in an open area covered in grasses and forbs? And so some of the other techniques that we're doing is we have these sensors called TMS4 from the Tom's company. They take measurements of soil moisture every 15 minutes. And so that gives us a reading throughout time, right? Volumetric water content throughout time. So we can see if it's changing based off of the seasons and throughout the years. This is an infiltrometer, and that's testing the infiltration rate of the soil. It has a perforated disc on the bottom and volumetric readings on the side. And so we time to see how fast that water infiltrates down into the soil. Two more volumetric water content sensors, right? So we have our PR2 sensors, which are buried to about 80 centimeters in depth. And so they give us different volumetric water content readings at different depths. So we can see if the water how that's changing at depths and if the surface conditions are really affecting it that much. And then the HydroSense 2 TDR, which is so it's a handheld probe. We go around the perimeter of each plot, and then we, like 50 centimeters, we take a measurement, and then we also record what plants are growing in that spot, so we can relate that in the shallow surface moisture content to if there's what plants are growing, and then we can also see how that's being affected and if that's changing based off of fire too. If the plants that were there aren't coming back, or if there's less recovery from that. We'll be able to see that. And just wanted to put in a picture of the burns because it was an exciting day. And unfortunately, when this presentation was set up months and months ago, we had planned to burn earlier in the season. And, as things go, it got pushed off due to various reasons, and we didn't actually end up burning until this last November. So I don't really have any data to show you from the post-burn, from our post-burn measurements, because we've only done one, but I will be showing, but I can comment on some of the things we've been seeing out there, and I will be showing you some of the other data from what we've seen in that as well. But getting on to that. So for the pre-burn water drop penetration tests, we have, so this is the preliminary data from our pre-burn water penetration tests. And the important aspect here, so just, I guess, and as an overview, we do them at the soil surface at 1 centimeter of depth and then at 3 centimeters of depth. And the higher the number, the more hydrophobic the water or the soil is, right? And the important thing the important finding from here is that there are hydrophobic soils present at this field site before the burn. And some of the areas that we have tested are very hydrophobic. We usually do the tests up to 5 minutes, and after 5 minutes we stop, kind of considering that it might just be evaporating at that point. And there are many times we've gone out there to test these sites. There have been measurements that we just cut off at 5 minutes. And most of them are underneath shrubs. So it seems like underneath the sagebrush shrubs tend to be more hydrophobic than in between the areas with like grasses and forbs and whatnot, right? And so to comment on what we have seen our first round of testing from the post-fire is that, so just like anecdotally, right, because this is just from one time going out and measuring these things, the fire has not increased the hydrophobicity necessarily, or at least it's not as clean cut as we originally had thought it would be. So some of the areas that were hydrophobic before the fire are not hydrophobic now. Some of the areas that weren't hydrophobic are hydrophobic now. And then, some of them just haven't changed at all. So it'll be really interesting to see going forward how that continues to develop and if there's any patterns that do come out of that. And maybe it will turn out that the fire does make it more hydrophobic, but that's yet to be seen. And this is going to be observed on a time scale of like, months to years, and hopefully years, as long as we can keep people going out there and keep measurements being taken of all of these things. And so just as a quick wrapping up slide, and I think I have a little bit of time left, so I can also show, before I do that, so just some of the volumetric water content readings that we get from the TOMPS, right? And this is temperature on the side. The orange is the corrected, calibrated one. So you can see that we are capturing good quality data from this field site. We do have quite a few spikes of precipitation, and there's also an eddy covariance tower out there that we can compare these precipitation values to as well. And so we'll be able to see how that changes too, and based off of proximity to shrubs or in the grass area. And so kind of wrapping all of this short presentation up, the main conclusions that we have and main important findings that we have from this are that we're starting with already water repellent soil, right? Some of the soil already is hydrophobic from the get-go, which you wouldn't be able to necessarily see if you're testing sites that have already burned, which kind of points to why this is such a valuable site experiment as well, because we have the pre and post burn data, and that the hydrophobicity is dependent on the vegetation, it seems, in the area. Is it shrubs or is it something like a forb or a grass? And so I think that land managers can use the findings of the study to plan and for planning and rehabilitation, restoration treatments after fire occurs, as well as to make better models that can more accurately predict how an area is going to change after fire occurs. To comment on that a little bit, the major goal too of this study is to make a model that can accurately predict how how water moves when these hydrophobic soils are present. So as it stands right now, there isn't really a good way to model that. We don't really have a quantitative way to model hydrophobicity in an environment and how that changes how water moves through that environment. There's some ways that you can get around it, but there isn't a quantitative way that you can directly point to and go like, this equation was made or this model was made specifically from these findings. And so that's one of the major goals or outputs that we have that we are hoping to get from this project, right, is to have a model or some quantitative way to actually show and calculate hydrophobicity in these environments. And then also potentially to increase the area of this study. So it's not just 20 small 3x4 plots, but maybe it's a larger area that this can be applied to and checked for validity, right? And so with the models so it says to better accurately predict how an area is going to change after fire occurs, with these better models, you could potentially prevent environmental degradation, decreasing water quality and flooding. The information for this hopefully will be available in 2027. Again, this project is 5 years running and some delays happened. But with that, I think that I will go to questions.
Great. Thanks, Connor. We have time for a couple questions. If anyone has them, put them in the chat. Um, Question, what is your hypothesis about why shrubs contribute to hydrophobicity? Could it be exudates from roots or salt contribution to soil from leaf drop?
I think that contributions from the leaf drop, that would be my hypothesis as to why it is more hydrophobic under the shrubs. Again, this isn't we're waiting for more data to come through, but anecdotally from when we've been going out there and testing these things, it does seem to be that the soil is more hydrophobic underneath those thick layers of litter. If there's not that thick layer of litter, it tends not to be hydrophobic.
Have you seen any relationship between fire duration or intensity to hydrophobicity?
So that one we're still waiting on data from. We do have quite a few plots though that were very low severity burns and pretty high severity burns, right? So like practically no mortality in the plants, and then everything's been obliterated. So hopefully we'll get some really good data on that to see if it changes based off of severity.
Great. Thank you so much. All right. If you have more questions, we can save them till the end. And now, Bianca Martinez will present. Thank you so much, Connor.
Of course.
Can you hear me?
Yes.
Great. So hi everyone. As Jeannie mentioned, my name is Bianca Martinez, and today I'll be presenting my research is specifically chemical speciation of burning from sagebrush ecosystem. Yeah, I'll get started. So wildfires in forest landscape are widely characterized. However, ecosystems such as the shrublands in the western U.S., there are dominant and poorly characterized. Studies have shown that in the last 30 years, more houses have been exposed to to shrubland and grassland wildfires than forest fire. You can see that we have a picture right here that shows specifically for the western region, specifically to Nevada. Um, so yeah, in the last 30 years, wildfires in the landscape has been more frequently, especially in areas of close proximity to people. And that is what we designate as the wildland urban interface. Fires in this area have been more frequent and resulting in rural communities facing disproportionate economic and safety risks. Thus, a comprehensive chemical characterization of this landscape is needed for fire research. Moving on to fire research, this is important because smoke is a major source of pollutants, not only of gases, but also of aerosols. They can trigger severe pollution events with substantial effect on public health. Since they contain many species, such as what you'll see here, we have PM or particulate matter, we have organic carbon, black carbon, but we also have other compounds such as carbon dioxide, carbon monoxide, and what we call VOCs are the volatile organic compounds. Specifically in this presentation, we'll focus on carbonyls. Here I have two examples, formaldehyde at the top and acetaldehyde at the bottom. These two are known to be carcinogenic and they're very reactive compounds that can degrade or produce other species. Not only they affect climate, they also have an impact on air quality. So we do have that, wildfire emissions and PM can be detrimental to public health, affecting in general, like cardiovascular system, respiratory, it can cause systemic inflammation or in extreme cases, damage to river activity. As I mentioned, they also degrade air quality not only on site, but significantly downwind, which can hamper efforts by air quality regulators to meet set air quality standards. Smoke emissions are affected by different factors. Here I'm presenting the combustion or the burning regime or burning conditions. So different processes. In this case, we have the flaming and smoldering. Here you also have a picture that shows the flaming, that it's characteristic, flames over the fuel. This process is relevant to wildfires. Usually wildfires take place when we have low moisture, low relative humidity, and temperatures as well. For smoldering, these are relevant to prescribed fires. So smoldering tends to have no flame, relevant to prescribed fire conditions. They tend to be with high moisture, low temperatures. Depending on the burning regime or the burning condition, emissions can be different. For example, we can have, if we have flaming combustion, they tend to be more carbon monoxide. Carbon monoxide concentrations tend to be higher. You do have that complete combustion, while for other compounds or other processes, for example, terpene content, they tend to be higher with uh, fresh and wet fuels. So now I'll move on to what we have been doing. So we have been working in the shrubland biomass burning. Specifically, we've been focusing on the four common fuels in the sagebrush ecosystem. We here have sagebrush to the left, rabbitbrush to the right. We also have been doing bitterbrush and horsebrush. For the sake of this presentation, we are presenting only, we're going to be focusing on carbonyls, which are not often characterized, but they're of great importance due to reactivity and health effects. So the carbonyls that I'll presenting today, so in the very briefly on the figure that you have to your right, the y-axis is for the emission factor. So we have the grams of pollutant, meaning grams of formaldehyde or acrolein or acetaldehyde over the kilograms of carbon emitted from the burn. For all of them, the x-axis has the different shrubs we burned. So overall, carcinogenic formaldehyde and acetaldehyde was the most dominant, which we got the highest emission factors. But overall, you see that there is variability among fuels and among the chemical compounds that are emitting or the pollutants that are emitted. If here I'm showing the carbonyl emissions, the speciation for the burning condition. So we have flaming in blue, smoldering in orange or yellow. So we have again the fuels on the bottom here. I only presenting sagebrush and rabbitbrush, and on the y-axis we have formaldehyde, acetaldehyde, and acrolein as well. There was no in for this a preliminary study. There was no significant difference in emissions, but you can see that both of the processes, either if it's smoldering and flaming, and within the fuels, you do see emission. You do see formaldehyde being released. We do tend to seem higher for formaldehyde and acetaldehyde, but you also have a list of other components that are not being shown in this presentation. Now moving on to management implications. So how can this research be used by land managers? So we have that this data can be used to improve fire behavior prediction by incorporating chemistry-based fuel parameters into fire models, meaning using what we have so that we're able to, see what changes. Also, they can prioritize high volatility species for targeted fuel treatment and informed restoration plan selection near wheel. So that is the wild urban interface. Also have the optimization of prescribed burn. So this is very useful for identifying optimal burning windows based on the fuel condition. We also have post-fire emissions and air quality planning. So together with models, it can be used to predict smoke composition based on dominant shrub chemistry, and also inform the community about smoke exposure mitigation strategies. Specifically in the wild urban interface, identifying low volatility native species, inform landscaping recommendations, and improve community wildfire mitigation. This research was supported by the National Science Foundation. We have here NSFF score, the HDRFS, and also OAL, which is Organic Analytical Lab, the lab that I work with, and we're at. So now I will take questions.
Thank you, Bianca. If you have questions for Bianca, please type them in the chat. Do your conclusions suggest recommended shrubs post-fire?
Can you repeat the question? Sorry.
Do your conclusions suggest recommended shrubs post-fire?
What?
Can you hear me?
Yeah, I can hear you, but I don't think I understand the question.
Oh, like
Can you
for
maybe phrase it
planting,
in a,
like
yeah.
if you're gonna plant shrubs after fire, if you're gonna do restoration or replanting after a fire, are there shrubs that you would recommend based on your results?
So based on the results, I would say we still need to gather, like more information about them because this is still preliminary. We do have a So depending on the shrub and depending on the burning processes, you might get different emissions. So if, recommending specific shrub for post-fire, I don't think I can answer that question. But within our component, within the project, we do have people in ecology that I think they're also looking at that, specifically post-fire. But yeah.
It looked like horsebrush was pretty toxic. Um, okay. Vera, it looks like you have a question, but you'll have to type it in the. Oh, go ahead.
Oh, yeah. Just very quick question. Bianca, great presentation. Just quick question. Do you know what the level of aldehyde concentrations, if there are any data from wood fires versus sagebrush fires, or it's something to explore more?
So that's a great question. Thank you. We are currently working on that. We have been looking at, natural fuels specifically. We've been doing chemical characterization. We do have carbonyls there. So we do have, the data for the natural fuels. For
Mm-hmm.
the urban, or if we're looking at that, wildland urban interface,
Mm-hmm.
we do have samples that we need to analyze for that. But yeah, that's something that we're definitely looking in because we do know that, they're very toxic and, they're very reactive by themselves. So they can even produce they can go on to the secondary production.
Yeah.
But it's a
Perfect.
work on progress. Yeah.
Yeah. That would be really interesting to see, like emission factors, Yeah.
Yes.
Yeah. Mm-hmm. Thank you, Bianca. Great talk.
Thank you so much, Bianca. All right, if you have more questions for Bianca, you can type them in the chat and we'll address them at the end. And now we'll hear from Jehren Boehm.
All right. Yep. Thank you very much. My name is Jehren Boehm, and I'm going to take you through technology for monitoring over large distances. Also, we like to call that distributed wireless sensor networks. So for the next 10 minutes, I want to take you through the future of on-the-ground monitoring. So I like to start with this graphic of the Sherwin-Williams cover the Earth. And we kind of have our satellites saying, right, aren't we there already? We have excellent satellite coverage pretty much everywhere on the globe, but we can see onto the surface, not necessarily under the surface. So it's not quite the final solution for coverage. So over above the Earth there, under the moon, I have a graph of the kind of different communication standards that exist. Cellular, which we know very well, Wi-Fi and Bluetooth, they all consume a lot of power. And that doesn't help so much for long range distance with low power, which is what we're going to look at with this LoRa protocol and standard. It's an IoT variation, Internet of Things, like we're used to for a lot of smart homes and a lot of other things that we use in our everyday lives. But this is aimed at industrial applications for long range and low power applications, and it's been around for roughly 10 years. And we're going to go into that a little bit deeper here. So LoRaWAN, right, stands for Long Range Wide Area Network. And we can see kind of the network topology here where there's a bunch of little sensors and they reach out to kind of a hub station, as we call it, gateway. And then those go back to a network server and an application server. which you can reach into and get the data. These little nodes use super special RF engineering magic, which kind of gets colloquially described as a chirp. So I kind of put in this bird with the chirp sounds here. And there's just a lot of really cool technology in optimizing the link budget for these small little battery-powered sensors so that they spend very little time on the air, use very little energy, and they don't conflict with each other, even in very noisy RF environments. And since they are just very well low-power packages, you don't really need to have any maintenance on these things for 3, 4, 5+ years, depending on how often they are transmitting. So let's go kind of to a use case for this. Soil moisture, we can see that from remotely sensed data here. What is going on here with 4-kilometer grids? We can kind of see it's wet on the left and drier on the right. But what happens when we kind of look at what's going on underneath there, right? Most of us should know Lake Tahoe. And we can see that maybe this satellite remotely sensed data isn't necessarily appropriate for the topography. So if we kick up the resolution just a little bit, down to 1 kilometer, right? This is snow water equivalent, not soil moisture anymore. And we can kind of see like a little bit clearer of a picture. But when we get even more closer to the ground, what people can cover on foot, we can see that, yeah, it's still pretty darn coarse and some more complex things could be happening. As you might have guessed here, this is not the same study site as HDRFS, but this is a different project similar to HDRFS, cyber infrastructure for sustained scientific innovations. And this is down in South Lake Tahoe. And here is a burn scar in black, right? This is the Caldor burn scar back in 2021. And I have a green circle and a red circle kind of indicating an area for closer investigation. And we can get a different look at that, right? Google Earth here showing us kind of right down the barrel of the Caldor burn scar. And we can see that, yeah, you have different intensity burns on these matching slopes. And so we want to use we want to create a multiple variable experiment here about the snow fire interactions between high and low severity burns using snow presence or absence at multiple depths, temperature, and soil moisture. And so to do this, right, it would take quite an effort of time to go into the field and do that, but we want to do it remotely after installing some sensors. And you can see up in the corner there, we have a little star indicating the gateway that we'll be having the sensors pass data through. And before, we dive out there and just throw sensors out into the wild and hope they work, right, we model the coverage of where the gateway can reach a line of sight. And we see that this site has a good promise for a reliable connection for these sensors. And here is just a picture that I took not too long ago, actually, and after a big snowstorm here in the Sierras. And you can kind of see just a clear difference between the two slopes. So we have expected eco-hydrologic differences between the two sites, mainly dependent upon the fire intensity that passed through there. So it's comparable in aspect, slope, distance to each other, geology, soil type, solar exposure, and variables like that. And here is kind of the test setup, the current test setup of our off-the-grid gateway using solar panels, batteries. We do have a Campbell Scientific data package out there as well, air temperature, wind speed, solar irradiance. On the left inset picture here, we have an example of our low-cost deployment, right? We have air temperature shielded up high. We have snow presence or absence using temperature probes at different levels lower on the pole. And then we have multiple soil moisture sensors at different orientations beneath the soil to capture different variables in soil moisture wetting and drying. And then our other inset picture is a quick look at the gateway, small little package, outdoor enclosure, 3 antennas, one mainly for the LoRaWAN protocol, the other one's for Wi-Fi. The panel here is the connection back to the Nevada Seismological Network that runs statewide through Nevada and a little bit into California. And now I can give you just a quick run through of how all of this should work, right? So we have our burn scar here, back to our 4 kilometer soil moisture remote sense data. We can see these are where sensors could be deployed on these 2 slopes. There's the gateway that it reaches to. And here's our edge of the internet at a fire camera site for the Nevada Seismological Network. And so these ones will transmit, and that gateway will send the data packets from those individual sensors into the edge of the internet, which will go through other microwave hops back to fiber and eventually to our data center on campus here at UNR. So here's just a quick look at how we can get a whole bunch of these sensors transmitting a lot of small data packets, temperature, soil moisture, conductivity, and such. And that's just the raw data coming through, kind of just seeing as is coming through live. But here's kind of a better look at the data portal in which people would interact with. There's logins and such, so people from different organizations can come in with different permissions. And also from some of the hard work from our colleagues in the computer science department, we can now data visualize on the fly. We can see kind of a spike in soil moisture from a recent rain at the end of February. And yeah, so that's an example of a localized example of using this LoRaWAN protocol off the grid near the edge of the internet as supplied by the infrastructure from the Nevada Seismological Laboratory and the Alert Wildfire Fire Camera Network. So you could also take a look, at your own sites and kind of think up your own exercise of what scale and resolution of monitoring needs would help for my unique situation. And if I got a price point for each of these sensors, how many would I need in order to make that resolution, spatial resolution, a reality? So you could hop on foot with a backpack full of these or in a side-by-side and go through the landscape and put your sensors into place and collect data long into the future. But yeah, this is the big overview of the statewide network for the Seismo Lab and Nevada SciNet. And this is kind of the vision that we could take this localized example down in South Lake Tahoe and expand it across the state to give a broader coverage to inexpensive sensors, expanding the Nevada Science Network. But this isn't quite a silver bullet. There are some caveats to this. And the biggest one is that it was developed for industry, not for mountain science and hydrology and fire science. But we've been really impressed with how it's been working. It's not necessarily sensors you can talk to all the time, right? They kind of shoot data out into the ether for gateways to pick up. And if there's no one there to pick it up, it's data that's lost. And there's just the realities of technology being placed out into the outdoors where stuff happens and data gaps do often happen. And these sensors are cheap, right? They are not like the same ones that Conor was using for his study. So we're kind of trying to figure out, are these comparable, or do they need to stand alone as their own monitoring network for different purposes and accuracy. So yeah, adapting this technology, we are using a vanilla setup of it. All of this is stuff that's easily available online at low price points and can be plugged in using open source technology to connect all the pieces together. And we're trying to fully figure out the strengths and weaknesses before we create custom fixes for those. But off this edge of the Nevada Seismo network, we do have our Red Rocks Road site, which we do have a gateway there for coverage. And you can see how, further north off into the desert, we are doing quite a few hops to get data back to the internet and the data center back here on campus. And here's a picture here where we're testing some of our lightweight gateway setups, so for rapid deployment, where you can see our experimental site over here, and there was an opportunistic opportunity to measure post-fire effects over at the Rancho fire, which happened after our site was established. However, there is no line of sight over this hill right in the way, so we do need to come up with a way to relay data, line of sight back and forth, and also open up opportunities for other monitoring efforts for anyone who wants to get involved. So for our future work, right, we do want to expand the coverage as much as we can over our state network. We want more redundancy in the data, trying to figure out ways to do that, and also inclusive participation for people that want to use this technology for long-term monitoring, because long-term networks of monitoring do matter a whole darn lot, right? So yeah, this thanks again. Here's all of the people and agencies involved. Nevada EPSCoR, Systems Computing Services, Seismological Laboratory, and the HDRFS and CSSI grants. Also, a Wild West grant for Wild Area Wireless Enabling Science Team. And with that, I'll open up for questions.
Thank you so much, Jehren. All right, we can take a couple questions for Jehren, and then we'll open up the broader discussion for anyone, questions for anyone. But first, for Jehren, how reliable is that transmission band? I think it is shared use. So would some locations have radio frequency interference that disrupts the data flow? Also, how much time onboard storage backup is typical?
Yeah, so typically there is no onboard data backup. Some brands do have a small amount available, but that is not universal amongst sensors that you buy. And yes, the 900 megahertz ISM band is open band, and there is traffic on it, yes. But back to the original black magic of this LoRa protocol, these chirps that are modulated are incredibly good at operating under the nose floor and encoding data, and then the gateway is able to pick that up and decode it. It comes down to the spreading factors for how much data is transmitted per each packet, and how much time is on the air. Those different spreading factors can deconflict, so that data is quite reliably transferred when there is connectivity, right, between the gateway and the internet. But yes, incredible RF propagation characteristics and noise floor handling.
Great, thank you. And if someone wanted to use these or try these out, what would they get in contact with you, or wait a year, or what's your suggestion?
Yeah, so again, we're just testing out the characteristics of how this is used in a vanilla setup with off-the-shelf equipment. We do have gateway coverage in several places. Certainly depends on where the coverage is, hoping to be found. There is quite a bit of work to be done to get coverage in certain places. But certainly we are, as the research engineering lab here at System Computing Services, we're always looking for opportunities to try to, get research done out there.
Great, thanks. All right, well, round of applause for all the presenters. Thank you so much for sharing your great work.